Hey guys, welcome to the channel. If you are a subscriber of this channel, then you already know how important the aperture of a telescope is. This is just not limited to the smaller telescopes we use. This also applies to the bigger telescopes we launch into space in lower Earth orbit. When you look at the sky from the Earth with your telescope, a lot of light is lost in the Earth's atmosphere before it reaches your telescope. That's why scientists decided to put the telescopes in lower Earth orbit, where there is no distraction of Earth's atmosphere. One of the best telescopes, which is in lower Earth orbit, is Hubble Telescope. This telescope was launched in the 1990s, and for the last 30 years it has served us well. Because of Hubble, we found so many objects in the universe. Hubble unleashed a flood of cosmic discoveries that have changed astronomy forever. Because of Hubble Telescope, we found that the universe is expanding. We found the presence of dark matter, and we were able to see the farthest point in the past as long as 13.4 billion light years away. Hubble also found out newly forming planetary systems in the universe and so many things. Hubble's aperture size was 2.4 meters. Though it has a big aperture and it's in the lower Earth orbit, it still has some limitation because of its aperture size and the way it was designed. To understand how Hubble works, you need to know what exactly light is. When we think of light, mostly we think about the light coming from the sun. In reality, light is nothing but electromagnetic radiation seen by the human eye, and we measure these radiation in wavelengths. These electromagnetic radiations occur on an extremely wide range of wavelengths, and out of their wide range, very tiny parts of wavelengths come under the visible spectrum, which we can see with our eye. The remaining entire range of gamma rays, ultraviolet rays, infrared rays, etc. is invisible to our human eyes. To see those wavelengths, we need a special instrument such as infrared goggles, a camera, or bigger aperture telescopes that can absorb maximum light. When the Hubble telescope was designed, it was primarily designed for studying optical and ultraviolet wavelengths, and it also had some infrared capabilities to study infrared light. Hubble can observe a small portion of the infrared spectrum from 0.8 to 2.5 microns, but its primary capabilities are in the ultraviolet and visible parts of the spectrum from 0.1 to 0.8 microns. If you look at the normal photo of pillars of creation taken by the Hubble telescope and the same photo with infrared light, you'll notice more details in the photo. In the normal photo, you can see the gas clouds, but in its infrared version, you can see the stars hiding in those clouds. Stars and planets that are just forming lie hidden behind dust clouds that absorb visible light. However, infrared light coming from the sources can penetrate through those dust clouds and reveal what's inside. When light is coming from distant objects, by the time it reaches the telescope, its wavelength is stretched from gamma rays to ultraviolet to infrared. This stretching of wavelength is called redshift. The light is pushed from the ultraviolet to the near infrared. The infrared spectrum is divided into three types: near infrared, which is 0.8 to 2.5 micron, mid-infrared, which is 3 to 25 micron, and far infrared, which is above 25 microns. So, to study those distant celestial objects in detail, we needed a bigger dedicated telescope that primarily works with infrared light. That's why scientists decided to make a James Webb Space Telescope. The early work of making this telescope started in 1996. At that time, it was named as Next Generation Telescope. In 2002, it was renamed as James Webb Space Telescope. The short name used for this telescope is Webb. In the initial concept design, the telescope's aperture was 8 meters. Then it was changed to 6.5 meters. Webb will examine every phase of cosmic history from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets to the evolution of our solar system. To make this telescope work, scientists had to think in very innovative ways. One simple thing you can notice is the main mirror is not circular but hexagonal, and it is made up of other small hexagonal mirrors. This is because the hexagonal shape is almost circular, and the smaller hexagonal mirrors fit together without gaps, forming a big hexagonal mirror. Also, smaller hexagonal segments can fold, which is perfect to fit the telescope in the rocket. If it were circular, then there would be gaps between them, and would be difficult to take into space. Before deciding on what kind of mirror to be used on the telescope, 2 test mirrors were built by scientists. One was made with beryllium, and the other was made with a special type of glass. After testing both the mirrors, scientists zeroed down on the beryllium mirror. Beryllium is lightweight, strong, and most important, it can withstand a wide range of temperatures. As the telescope will be in deep space facing minus 250 degrees plus temperatures, beryllium is the most suitable material for the telescope. Another challenge scientists faced was to keep the large mirror cold. The telescope is designed to observe the infrared light of the first stars and galaxies in the universe. If the telescope's mirror got hot, then it'll give off infrared light and the light coming from those distant galaxies will be lost. So it's very important to keep the mirror of the telescope cold, to protect the telescope from external sources of light and heat, as well as from heat emitted by the telescope itself. It has 5-layer tennis court-sized sun shields that provide shade. The sun shield is designed from a special kind of material that will cool down the telescope. One side of the sun shield is hot, the other side of the sun shield is cold. The temperature difference between the hot and cold sides of the telescope will be huge. You could almost boil water on the hot side and freeze nitrogen on the cold side. Also, to help to maintain the temperature of the telescope to minus 250 degrees and to increase its efficiency, it will be sent in deep space. The telescope will be at Lagrange point 2, also known as L2. Lagrange points are the points in the space where the objects stay in a steady position. This happens because at any Lagrange point, two bigger objects are exerting an equal amount of force on that point. So, both forces get nullified and the object in the position remains steady. The distance between the Moon and Earth is 384,000 kilometers. The distance between the Earth and Webb will be 1.5 million kilometers in the exact opposite direction of the Sun. Some of you might think if the telescope is so far away from the Earth, then wouldn't it take more than a year to orbit around the Sun? In a normal scenario, this will happen, but here comes the beauty of L2. Because the Sun and Earth's gravitational pull is balanced out at L2, it will keep up with the Earth as the Earth orbits the Sun. At L2, Webb will orbit around L2 and not sit stationary, so we'll need a little rocket thrust to keep it in orbit in L2. The Sun, Earth, and Webb telescope will always be in a straight line path. The telescope's sun shield will always facing the Earth so that all the light and heat coming from the Sun and Earth is blocked by the sun shield, maintaining the telescope's temperature. With the Sun and the Earth in the same part of the sky, the Webb telescope will enjoy an open, unimpeded view of the universe. In comparison, the Hubble Space Telescope is in low Earth orbit, where it goes in and out of Earth's shadow every 90 minutes. Hubble's view is blocked by the Earth for part of each orbit, limiting where the telescope can look at any given time. This will not be a problem with the Webb telescope. Another advantage of keeping the telescope at L2 is the ease of communication from the Earth. As the telescope will always be at the same point in space, it'll be easier to have continuous communication with the Webb through Deep Space Network. After the launch, it will take roughly 30 days for Webb to reach the start of its orbit at L2. Webb will begin its science mission and start to conduct routine science operation after 6 months. How much this has cost so far? Initially, when the concept of this telescope surfaced in 1996, the budget for the whole project was $500 million. But this is space exploration, and every single thing we send to space has to go through rigorous testing. Because once you send it into space, then repairing it is not a feasible option. So every single minute part of the telescope has to go through rigorous testing. And even if there's a small doubt, you need to reinvent things to make it work for the long term. So from 1996 to 2010, the budget of the telescope has gone from $500 million to $6.5 billion. By the time it finishes the telescope, the overall cost of the project will exceed $10 billion. James Webb Space Telescope will be able to look much deeper in the past, beyond the point of the Big Bang, and will learn how the primitive planets and solar systems are formed. Overall, we'll get a much closer and deeper knowledge of the universe once this telescope will be working. We'll also be able to find how life began on Earth. Scientists believe that the chemical elements of life were first produced in the first generation of stars, after the Big Bang. We're here today because of them. We have yet to observe the era of our universe's history when galaxies began to form. We have a lot to learn about how galaxies got supermassive black holes in their centers, and we don't know whether the black holes caused the galaxies to form or vice versa. Also, if we want to know how the little planet Earth came to be capable of supporting life, we need to measure what happened at the beginning, and the James Webb Space Telescope will help to do that. It might also help us get the answer to a very old question: are we alone in this universe? This telescope is going to help us find out very exciting things about the universe. I hope you liked this video. If you did, then give it a like and subscribe to the channel for more content. See you in the next video. Have a nice day, guys. Peace.